So I'm sorry I couldn't make it in person there. I tried my best. So yeah, let's start. I'm Omer Hassan. I am a PhD student in Till Ole Bergman's lab in Mainz. I'm also the lab manager here at the Leibniz Institute. And in addition to that, I am head of software development in Sing2Brain, which is a startup basically building the real-time EEG triggered system. So before I kind of dive deep into my talk, that how we are using TMS and EEG combination to build some novel work, I want to explain the basic active systems memories consolidation theory, or just explain how sleep-specific oscillations plays kind of an important role in long-term memory formation in humans. So during non-REM sleep, non-rapid eye movement sleep, the exceptionally low cholinergic tone enables the emergence of very highly synchronized oscillatory activity in thalamoneocortical hippocampal system, which is famous as slow oscillations and sleep spindles and hippocampal ripples. So these three oscillations are kind of generated in this thalamoneocortical hippocampal system, and they systematically interact with each other, and then therefore they are assumed to facilitate some systems level memory consolidation and help in long-term memory formation. So the neocortical neurons population synchronously alternate hyperpolarization and depolarization states and give rise to very synchronized low frequency, less than 1 hertz oscillations, which are known as slow oscillations. Then moving forward, using through the corticothalamic projections, the slow oscillations triggers sleep spindle, which are oscillatory events of waxing and waning happening at 12-15 hertz, and they're generated in thalamus, and they then project into neocortex as well as motor cortex. And just like the way the slow oscillations triggered a spindle, the spindle indeed triggers the happening or occurrence of a hippocampal ripple, and this hippocampal ripple is kind of has been shown in animal work very nicely to represent the reactivation of hippocampal memories. And yeah, so we can conclude that the sleep spindle is kind of connected to all of this story. So the slow oscillations generate sleep spindle, and the sleep spindles generate hippocampus. So spindle is in center of this entire web that we're talking about. And we assume that it is a key element that opens the windows for plasticity that enables a long-term memory formation by means of this highly synchronized thalamocortical input that actually enables this calcium influx into the cortical neurons that is very important for spike timing dependent plasticity. And the overarching goal of neuromodulation is for at least us is to generate this or exploit this spike time independent plasticity in humans non-invasively in a reversible order likely. So therefore we decided to study the spindles indeed with the help of TMS EEG studies. And yeah, and here we basically so in summary that all of the sleep and memory research converges to this notion that the phase and amplitude coupling between the slow oscillations and the spindles, and also the spindles and ripples, is important for the synaptic plasticity and rescaling of the weights, and therefore the long-term memory formation. As you can see here on the panel D, I don't know if you can see my mouse or not, or my cursor or not, but I'm trying to show you here that that the phase. So we propose that the phase dependent EEG phase dependent RTMS mimics this procedure of enhancing the phase amplitude coupling, as has been shown in animal work invasively, that there is a theta gamma coupling that is associated with higher spike rate as shown on panel C. So indeed, we say that with the help of RTM, phase triggered RTMS, we might be able to induce some phase or enhance some or decrease some phase amplitude coupling between at least low oscillation and spindles, and thereby control this entire story. So we wanted to move on with this hypothesis and this background, and we designed a study in humans using TMS EEG. So we decided to stimulate on different 6 time points during non-REM sleep using TMS, single pulse. And we wanted to know, first of all, that before we actually target the sleep spindle in our TMS, we wanted to know which phase is actually then important, because the spindle as a whole is kind of known to be very important for memory consolidation, but it's a long event of 2 seconds, and we want to start at some point to give the TMS pulse. And we have seen in studies from Christoph Renner that the phase actually matters and it helps in efficacy of the plasticity induced. So we decided this to do the study, and we in non-REM sleep chose 6 different time points. One is a time point that's shown here in red, in which no spindle, slow oscillation, or K complex is happening, and one is which happened just kind of 1.5 seconds afterwards. A spindle has occurred, and then there were 4 different time points within an ongoing spindle. So it's rising, peak, falling, and trough. So these were the 6 conditions that we chose, and we decided to do single pulse TMS and then measure MEPs to quantify the excitability inhibition profile of the spindle. So here you see on the top the experimental setup. The subject came into the sleep lab and slept for a night, and we locked their neck for a while and did neuronavigated TMS, measured MEPs from different muscles, and also recorded EEG simultaneously to do this real-time targeting. So before we actually move to that step, we first started by optimizing the setup, because TMS during sleep is not really easy, although it's even not easy while wakefulness. But when participant is sleeping and then doing a neuronavigated TMS is problematic, because you have to lock the neck of the person, and then after locking the neck of the person, from here the subject of course cannot sleep as comfortably or as long or as necessary for the experiment. So we are talking about at least 2 hours of sleep, and in this circumstance here you see many people couldn't sleep for less than more than an hour or so. So then we wanted to do this kind of a mini robot project that's a semi-robotic arm that could take control of this positioning of the coil of the TMS, and some other kind of stimulation modalities. But yeah, so we know that we have this Exilium cobot present in the market nowadays, but that's too big, and that's not able to do the stimulation in the supine position. So when you are upright, then yes, it's possible. And when the person is like absolutely in a sleep-like state or in a spine position, then it's these robots, commercially available robots for TMS today now don't work actually. So we launched this project. This is ongoing. We hope to finish this very soon as well. But I just wanted to highlight you. But we still, because we didn't want to wait to complete this project to move on to the actual physiological hypothesis that we had. So then we just did we tried to improvise the setup and lock the TMS coil to a neuronavigated motor hotspot using the mechanical arms provided by MagVenture. And then whenever the participant woke up, so it's an art that how do you do sleep TMS, but we were able to we collected 20 subjects, 2 different nights, and yeah. So before we actually also went there, we then, as I shown you earlier in the experiment design, that we want to target the sleep spindle, and there had been no good solution available in the market or available in research literature that could help us in there was no ready-made solution to detect the sleep spindles. So we then just built our own algorithm, which is called as real-time spindle detector. So it just depends on last 500 milliseconds of data. And then we show here that using the F1 scores, our algorithm performed equally well as compared to offline algorithms. And we compared it with 3 different offline algorithms, and the offline algorithms, when compared with themselves, performed almost like at 80%, and our algorithm also performed at 80% with for NAV for a full night, and with or without the sleep scoring information. So we sorted this out. This paper has been now accepted and actually published in Journal of Sleep Research. Here I show a little bit more mechanism into how I built this algorithm. So typically, the major problem is that this is the rot phase. A spindle happens, and most of the spindle studies, even offline, and only very few of those that were online, just detected this sigma band envelope, which is shown here in the green color. And whenever it was above certain threshold, they said that it was spindle. And the problem is here, this is that you will have a lot of false positives. So then we included more heuristics, correlation, frequency bounds, relative power, and then we show that, okay, we could really target very local spindles, and they had like very typical time frequency boundaries. So given that this was done, we moved on to also show that the phase targeting can be actually performed properly in this detected spindle, because spindles are, so this has been also never discussed or done in the literature, and that real-time phase targeting is also kind of not very easy to do, and we were the first ones to tap into this area. And we wanted to make sure that the phase is not biased, because it's usually right, the spindles are co-occurring with slow oscillations, and they are on the up state, locked up state, and so that might not work with the traditional phase targeting, phase estimation algorithms. But well, we were lucky, the available phase detection algorithm built by Christopher Renner were able to still detect the phase of a spindle reliably, and here we show different phases here. So yeah, then here I showed you these novel results of what it was the outcome. So we targeted on different 4 phases and pre and post spindle, and we measured using TMS single pulse MEPs, and we found out this interesting story that as compared to post-pre, which is just a general baseline, we found that, okay, yes, there was an overall inhibition of MEPs happening during different phases of spindles. Here you see in gray the phase of the oscillation. The left graph here where is normalized data, and here is the actual raw MEP data. And we were able to see the effects on both the levels. On usually in these kind of real-time phase trigger studies, results are shown in only normalized form, but we were in this case also able to observe them in the raw data, so raw MEP data. And we found out that the falling flank is actually where the most inhibition is happening during a particular spindle, and then trough lead to following the falling flank is where this kind of excitatory or disinhibitory effect has just arrived back. But although it was not more than what the baseline had, and here you see the same results on the raw level. So this was quite interesting for us, that okay, yes, there is a time point within an ongoing spindle that might be more important. So then we were not sure that why are these effects happening. We wanted to have a better control on these. However, here you see the similar comparisons of MEPs. So these are subject MEPs, 20 subjects, comparison of trough, falling, rising, falling, peak falling, post falling, and pre-falling. So you see always this inhibitory effect happening whenever the falling flank is coming up on a single subject level as well most of the time. So we actually concluded here that the phase of the spindle modulates the cortical excitability for sure, but we wanted to apply some control analysis. So we then run this control analysis with cluster-based permutation tests that does the voltage of a spindle in a particular condition of trough browsing or poike walling cause a problem in this kind of um, asymmetrical MEP results. So we found out in that neither the voltage, neither the sigma power of the last 500 milliseconds when the stimulation happened, neither the frequency of a particular trial of a spindle actually had any impact on the MEP. So these are the correlation graphs with the single trial voltage, sigma power, frequency with a single trial MEP. So we really found no difference of these, no impact of these parameters on the MEP. So indeed, the results were coming up from the phase of the spindle. We also moved on to find out if the 1/f level or the duration of the spindle, because the spindle happens from 0.5 to 2 seconds long typically, and we did trigger somewhere in between or just slightly after in between or just slightly before in between. So we were not sure if that might play a role in this. And then the maximum voltage that the spindle have. So indeed, all of these 6 control parameters had no impact on the MEP. So there was no significant correlation between these 6 parameters and the MEP amplitude that we measured across all the channels, all 64 on the scalpel. So this shows that this was, so that's our control analysis. Moving forward, the topic of today is the TEPs. So we did also, of course, measure the EEG after the TMS as well, and then we found out very interesting results that are somewhat similar to what when Till did 10 years back his slow oscillation triggered a study on up and down states. He found that when a stimulation happened only on the slow oscillation phase, then only a slow oscillation triggered. But we found out interestingly that when we trigger during spindle, we observed high frequency sigma-like activity even in very early time points from 0 to 500 millisecond, but from 500 to almost 1.5 second, we do see a very nice K complex, and this differs in its topographical states and amplitudes and things. So we are still analyzing this region. This was not the major goal of the study that we actually, but indeed it does modulates the thalamic excitability, and since so sound masking was applied, we tried to control the confounds of the TMS. EEG measurements or DEP measurements, of course, in sleep we cannot do as rigorously as in wakefulness, but we did apply the sound masking as much as possible and did use some level of control for the somatosensory sensations. And we do want to be careful while interpreting these results that how does maybe the phase amplitude coupling is enhanced at a particular phase or so, although it is expected to enhance only after an RTMS session, but maybe a single trial level does this. So we're still exploring this region, but I wanted to show you with this. Yeah, so with this I just uncovered all of our sleep triggered sleep spindle triggered EEG-TMS studies and results. In addition to that, I also want to talk a little bit about best toolbox, because this also has this one feature to real-time TEP studies. So 3-4 years back when I started my PhD, I started developing this toolbox with my collaborators, and the idea was to have a graphical interface, a nice software that can be a house for designing the brain stimulation experiments. So here you see on screen some screenshots of the software. You can configure multiple input-output devices, and it shows you the results online, and also you can pause or stop it. So currently this is compatible with on a very limited number of devices, although we try to expand the horizon of the number of devices. And since this is a software that integrates with hardware and other softwares, so it does not work as smoothly as just any other offline analysis software. So the more information is available here on our website. We try to expand this in next years, and of course it's an evolutionary process here in this case. So here just similar, some small results from some TMS, EEG, EMG, EEG measurements of the toolbox. But I do want, so the toolbox can do also the dose response curves, paired pulse, single pulse, and then you can ideally use these outcome results in subsequent protocols without needing to worry about the actual values. And yeah, so you can do like this. So our this previous TMS EEG study we did using the best toolbox. So you could also target on different oscillations with the help of a real-time device. And yeah, so here I show the real-time TP measurements. So using best toolbox, you can also do real-time TP measurements and see different topographics, updating every trial by trial, and certain butterfly plots and single averages. You can so there's this interface available for doing the real-time TP hotspot search or real-time TP measurements. Yeah, so I want to just highlight the achievements that had led me to out of this work. So the best toolbox went to the cover of brain stimulation. Then I also won BrainBox Initiative Conference post prize for the best toolbox, and the sleep study that I presented to you recently got the first poster award from ICCN in 2022 in Geneva. And with that, I would like to thank you, my team, and my team at Till's Lab here, and my team at Think2Brain in Tübingen. And yeah, without the help of these people, I would not have actually been able to do all of this work. Yeah, I hope I'm in time. I didn't take it.